So yeah, welcome and thanks for coming. And I'm excited to see so many smiling faces today. I'm just gonna switch screens for a moment, and I will then just give you a bit of an introduction. So my background was actually an ME/CFS patient that recovered some 30 odd years ago. History of certain, medical things that sort of followed on as I was clearing out the remains of that period in my life. But ultimately, then a successful career, four different engineering disciplines with a side of biochem, endocrinology, pharmacology, and I was raised by a pair of naturopaths. So my background I have a foot in both camps. I can see the problem from both sides, and ultimately the solution that needs to bring all of these things together. So that's kind of my role is just to try to fill in the gaps and sort of illuminate a model that explains all of these things and then allows people to actually make some very good clinical decisions and help actually bring the patients out of the situations that they're in. If you've seen some of my biochemistry work, you'll probably have noticed that I like diagrams. A lot of that's come, I think, from the engineering background as much as the biochemistry background. So the way that I see things is ultimately through an engineering lens. A lot of the diagrams will be initially perhaps a little complicated. Some of the diagrams are less complicated. I've tried to highlight mechanisms and intersections that are kind of essential to understanding some of these things in hopefully easier ways. And then that kind of leads into some of the more in-depth biochemistry. So what I'll do without further ado is switch over to a couple of the tools. So one of the tools, and this is my favorite, is the metabolic pathway overlay tool. What I might do is actually just start off with some of the simpler diagrams and talk about how this tool can be used with your oligoscan data and your organic acid test data, whichever panels you happen to have. And you can use this as a bit of a dashboard to get a feel for what's happening in the patient before diving into some of the more difficult things here. I'll just bring this up. So this is figure 14 from the disease modeling page, and what it represents is essentially the NAD redox, the mitochondrial metabolism, the inputs coming from the methylation pathway and transsulfuration pathway, what that actually means as far as the glutathione metabolism is concerned, why the glutathione metabolism is so critical for the mitochondrial metabolism, but also for heavy metals and mycotoxins and various other things that are accumulating, and also what happens with the microbiome in part of the response in most patients when basically this cascade is present. So taking a step back before I dive into this, there are a few things. Fundamentally, what the model is describing is a complex cascade where essentially a series of different events and progressive, I feel like traumas, insults, heavy metals accumulation, mineral deficiencies, dietary inadequacies, toxin accumulation, things basically lead to a progressive cascade where ultimately the mitochondrial metabolism and the related pathways get progressively more impaired. And so in that context, you could be looking at, for example, childhood trauma plus a number of other things that leads to, let's say, complex PTSD, the nervous system being unable to achieve regulation, so being able to regulate in difficult conditions. That perhaps also including some different forms that we could talk about with autism spectrum disorder, ADHD, and various other things as part of this cascade. Ultimately, a microbiome adaptation, so fermentation syndrome, which is trying to regulate part of that sympathetic excess, and I'll talk about that in a little while. And then the cascade ultimately that's leading to hyperoxaluria, connective tissue disorders. You'll see a number of things like elevated B6 in the serum, perhaps vitamin A, elevated cholesterols, which is all symptomatic of the NAD redox issues that we're seeing here. I'm going to go into some more detail, and essentially sympathetic excess, loss of parasympathetic signaling and metabolism. Fundamentally, one of the big things about the metabolism and the nervous system is that the parasympathetic signaling requires localized energy storage for it to operate. So what that actually means is that the glycogen homeostasis is a critical piece of the parasympathetic balance. So if the glycogen storage has been impaired, then all that's left to keep the cells ticking over is sympathetic signaling and the various different cascades. So the catabolic energy systems, beta oxidation, lipolysis, all the things that basically require adrenaline and CMPKA to keep the cells spinning. So in this context, one of the things which then leads to sympathetic excess, and it can come from a number of different insults. It can come from a number of different factors, but all of these different things are going to combine to progressively lead to sympathetic overdrive. And then a layer, well, many different layers of compensations and things which are trying to regulate this and restore homeostasis, but ultimately certain variables which are leading to persistence and stop the cascade from self-correcting. And some of that is going to be biochemical, some of that is also going to be emotional regulation, trauma, etc., and essentially autonomic nervous system dysregulation, calcium channel dysregulation, glutamate dysregulation, and a whole complex cascade downstream of all of this. So diving into one of the key mechanisms here is this glutathione metabolism. And so why this is kind of critical is because essentially the glutathione metabolism is one of the things which is going to regulate the oxidative stress, so essentially the reactive oxygen species generation from the mitochondrial metabolism, but also from immune activity, various other things. And the glutathione synthesis is actually reliant on the methylation and transsulfuration pathways to generate the glycine and the cysteine, which is required to produce the glutathione. So if we have, for example, low zinc, low choline, low serine, to a number of other things, low active B1, a number of other pieces, we're going to lead to problems with methylation and problems with transsulfuration, and ultimately either or low glycine, low cysteine, and then ultimately low glutathione potentially, but also eventually we're going to lead to this low glutathione redox. And then you'll see little hints for this when you're looking at, say, for example, a mosaic or other organic acids tests. You might get a classic alarm bell like the pyroglutamate levels being high, which is the overflow when the glutathione metabolism is impaired. So different tests, different organic acids tests have actually got different resolution, different levels of detail. So if you're looking at a mosaic or a nutripath, for example, there's a very different level of resolution because the nutripath, for example, has less analytes. Then we can move up to the OMX, for example, that has more metabolites, that's in between. And then there is the theriome Aristotle, like the classic or the plus, which gives you quite a level of depth of resolution and breadth. So we're going to look at all of those different tests and what that looks like in the context of the tools and the pathways for information. So when we're looking at this intersection, the hypothesis is, and this is the pattern you'll see time and time again when you start putting your patient data through these tools, you'll see that ultimately we'll have dysregulated glutathione. So in this case at the moment, despite the fact that we actually have low glycine and low cysteine, there is elevated reduced glutathione. This particular test doesn't give us the oxidized levels as well, but the theriome Aristotle plus actually gives us both. It makes it a lot easier to see all of this. But what we're seeing is essentially that glutathione, it needs to go through an enzyme called glutathione peroxidase, which many of you I'm sure are very familiar with. And that creates the oxidized glutathione. And then there is the redox going through glutathione reductase, which then recreates the reduced glutathione. So in the context of the metals and the minerals, what that means is that if we have, for example, low selenium, that's going to be affecting the glutathione peroxidase. Also thyroid function for T4 to T3, but I'll come back to all of that later. So when we're then looking at the heavy metals, if we've had, because of low glutathione over a period, and just daily general exposure to the different heavy metals. Like there's going to be heavy metals in all of our foods and just the general environment. And the certain inflammatory cascade that I'm going to go into in a little while is going to essentially trigger the accumulation of these heavy metals in the brain, the liver, the kidneys, the spleen, and lead to just this progressive accumulation. So in that context, we have mercury, for example. We have silver. Both of those are responsible for kicking the selenium off glutathione peroxidase and various other enzymes. And then on the other side, we have cadmium and lead, which are responsible for inhibiting glutathione reductase activity. And what happens there is essentially that if once this becomes progressively more and more impaired, that means that the automatic quote unquote cooling system, so the oxidative stress regulation coming out of the mitochondria, becomes progressively inhibited. And so what that means is essentially is that the mitochondrial, the TCA cycle is going to become progressively inhibited whenever it's under load. And the way that it triggers that is essentially the NAD status between the two pools. So if we have a slightly closer look at the TCA cycle and some of the related enzymes, what we'll see is that, okay, we have pyruvate dehydrogenase, which essentially is making the acetyl-CoA. And then the the dehydrogenases inside of the TCA cycle. So isocitrate dehydrogenase that takes D-isocitrate, makes alpha-ketoglutarate or 2-oxoglutarate. We then have the alpha-ketoglutarate to succinyl-CoA, so that's the alpha-ketoglutarate dehydrogenase complex. And then on the other side of the cycle, we have malate through to oxaloacetate. And so those enzymes normally will take NAD, make NADH, and then that NADH ends up being metabolized by complex 1, so NADH, dehydrogenase, and that takes the H, shuttles the electrons off in the electron transport chain through ubiquinone, ubiquinol redox, and returns that NADH back to the pool. So that keeps the balance. However, if there is too much quote unquote engine heat, so in other words, if the mitochondria are generating too much in the way of reactive oxygen species, or if there are external factors like the immune response and various things creating peroxynitrites, like various other things which are contributing to the overheating or oxidative stress, then complex 1 and complex 3 and others will be progressively inhibited, which then means that this NADH pool elevates. So when that NADH pool elevates, it's going to trigger a number of things to happen. So one of them is that the glutamate here, so glutamate dehydrogenase, starts generating glutamate. So alpha-ketoglutarate, halfway through the cycle, or the first half of the cycle, it's really 2 cycles that are connected. That glutamate, when it's inside the cells, is actually a trigger to regulate the synthesis of glutathione. So that's the other cofactor we need, glycine, cysteine, and glutamate to create glutathione. The other thing that happens by NADP transhydrogenase is that we end up converting NADP to NADPH. So the H from the NAD and NADH pool ends up getting stuck onto the end of the NADP to make NADPH. Now that drives the NADPH for the glutathione reductase activity. So this elevation of glutamate inside the cells and NADPH inside the cells essentially powers the glutathione synthesis and redox to then deal with that reactive oxygen species load by glutathione peroxidase activity, and then essentially restore the normal operations of the citric acid cycle and the electron redox via NAD redox, etc. So when that doesn't happen effectively, because we have problems with the glutathione metabolism, and look, there are other things which like MNSOD, CUZNSOD, other things which are also participating in that overall oxidative stress metabolism, we start to see overflow in the other places. So one of those is lactate dehydrogenase. And so that's essentially going to take the pyruvate that's there and convert that into lactate. That's participating in converting NADH back to NAD to try to restore the balance. Outside in the cytosol, there's also GPD1 and 2, and that's going to take the DHAP and turn that into G3P. Ultimately, you'll see that as an elevation of glycerol if you have a theriome or other test which is measuring glycerol, and you might also see the elevated triglycerides in some circumstances if you're looking in the serum data. So these are all basically indications for the NAD redox becoming progressively inhibited for whatever reason. There's an additional mechanism for the lactate dehydrogenase via prolyl hydroxylase inhibition, which also then promotes the expression of LDH, and that's part of this hypoxia-inducible factors 1 alpha metabolism. It's like a fault sensor for the mitochondria and TCA cycle. I'll jump into that a little bit later, but just to let you know, there's some additional mechanisms here which aren't exactly shown in this diagram at this point. So what the net effect of all of this is that essentially you then have regulation from this downstream of this set of faults, which then triggers an inhibition of other pathways. So the substrate pathways to the TCA cycle. So everyone normally learns about glycolysis as the primary input to the TCA cycle. So essentially you have the glucose being picked up. There's also the glycogen storage. I'll come back into that. The end of that pathway ends up at pyruvate, and then pyruvate ends up at acetyl-CoA. I'll jump to another diagram in a moment and I'll show you all of that. But there are also a range of other pathways that feed the TCA cycle. So we've got the fatty acid transport and oxidation. You've got the glutaminylases. You've got the branched chain amino acid catabolism. There are a number of other little feeder pathways and anaplerosis. So things like the GABA shunt, and there's also an input from fumarate. There's all these different little ones depending on the cell context. What this diagram essentially does as a bit of a dashboard is actually also just, you can see here when we have that data, it'll actually show, hey, if we've got low serine, if we've got low carnosine, this particular one has low hydroxybutyrate, 2-hydroxybutyrate, but there's a reason, I'll show you that. But if that's high, that's a very good indication that there is a really significant inhibition, and it's actually used to shut down the branched chain amino acids. So in this context, we can get a bit of a view from the patient data of what's actually going on around this key intersection. And then there are outputs from here out to other pathways. So once this intersection starts becoming inhibited, it has knock-on effects to other things. So some of the synthesis pathways, which I'm going to go into in a minute, include the pyrimidine synthesis. So that's the uridine triphosphate, which is used for glycogen homeostasis and synthesis, and inosine, which is actually, if you've looked into Navio or any of the extracellular purinergic signaling, so extracellular ATP is one of the alarm signals that cells can use to alert neighbors that there is some sort of, dire, calamity going on. So it could be like a wound, it could be nervous system dysregulation, a range of things that can be causing all of that. And that is gated by this level of inosine. And for various reasons, once this cascade is now inhibited, it means that it's dysregulating that cell danger response. So a level 1 alarm might be getting seen as a level 10 alarm simply because this pathway is inhibited. So we can start to see that, and I'm going to dive into that later, but that's just a little taste of things to come. There is also another little diagram here, which is figure 12, which is another good dashboard, but it also explains some of the mechanisms for how the minerals become low, how the heavy metals are accumulating, and that thing that I mentioned before about the prolyl hydroxylases essentially being a major fault sensor. It's also the thing that triggers the chronic reactivation of the herpes viruses, HPV, HIV, any of the latent lytic viruses. They take a feed from this particular signal. So the same alarm signal inside the cells, which triggers anaerobic glycolysis, happens to be the same signal that triggers the viral reactivation. So I'm just going to take a little zoom out for a minute and then sort of look at these blocks, and then we'll dive perhaps into some of the blocks in a little more detail. So mitochondrial dysfunction is a broad term. There can be many different things that are going to create mitochondrial dysfunction. We just touched on a moment ago, for example, the oxidative stress being a primary inhibitor. But there can be a range of other things. There can be, for example, cofactor deficiencies. We could have low magnesium. We could have problems with iron sulfur clusters in some of like the complexes and things like that. There could be hypoxia. There could be a range of different things which are going to trigger a fault. So the metabolism has these sensors which basically pick up all of these different states. And when those states are present, it triggers a shift away from mitochondrial metabolism to cytosolic lactic acid redox, and using the glycolysis pathway to essentially generate the ATP. So it's essentially a fault sensor. Hey, if the mitochondria got a range of different issues, stop using them, calm all that down, and in the meantime, start using lactic acid metabolism. And that's all well and good when there aren't deficiencies and other problems. But when this is used or overused, it leads to renal wastage of the electrolytes by acidemia and hyperoxaluria under a certain condition. So when the LDH is promoted, while there's P5P and problems with certain transaminations and things, we end up with elevated oxalate and low glycine. So I'll go back into that one a little bit later. But ultimately, the progression of this cascade turns into a bit of a spiral via the acidemia. So essentially, the acidemia is going to be triggering the loss of the electrolytes and zinc. And on the other side of this, it also has this inflammatory cascade via certain cytokines. We have IL-6 as being probably the largest signal, tumor necrosis factor alpha, IL-1 beta, 22 and 10. Those are in order of importance. Each of those are able to then trigger an elevation of a peptide hormone called hepcidin. And hepcidin is mostly known as the master regulator for iron metabolism, but it also happens to regulate 12 minerals and metals. So if you're seeing chronically low ferritin or iron dysregulation in general in your patients, it's the canary in the coal mine, because when you start looking at the other data, you're going to see that there are a number of other deficiencies also present. So the same transporters which transport and regulate the iron homeostasis are also responsible for all of these other minerals and these heavy metals. And so this is where this glutathione metabolism that we just looked at before becomes highly relevant, because every time we have this back and forth signaling from this cytokine elevation, and then what happens is the body intentionally sequesters the minerals and metals out of the circulation to deprive any invading pathogens, presumably, of the benefit of those minerals or proliferation, and it also sequesters the heavy metals. At the same time as it does that, it also blocks the dietary absorption of these minerals and metals in the gut, in the duodenum. So different cells have different contexts. Some of them only have DMT or ferroportin. The ones in the gut have both. So when the hepcidin levels go up, it blocks the dietary absorption, and progressively over time, if they've got a chronic infection or chronic inflammatory cascade, then you'll see the progressive loss of the minerals over time and the progressive accumulation of the metals in the cells. That said, the problem is going to be is that the quality of your data is what is actually going to illuminate this cascade or not. So if you're looking at hair toxin mineral analysis tests, for example, you're only going to be seeing, because those cells don't actually have the transporters, you're only seeing the high tide mark or low tide mark of what's in the serum at the time, and you don't really get a good feed for what's actually going on. So you might actually see lower levels of heavy metals in the hair and the urine, because it's not actually getting excreted out of the cell. It's accumulating in these other cells, and then you'll start to see that shift later when you start repairing the glutathione metabolism, or if you're using various different heavy metal chelators. Progressively, though, you will see, I mean, one of the things you'll see in the hair test is you will see the deficiencies of these minerals, because ultimately that's what's happening in the hair. So, but you won't really capture the true state of the intracellular status. So that's why the oligo scan is quite important, but you can also use other white blood cell, like, because they've got mitochondria, white blood cell type testing, so that you've got vibrant wellness micronutrients, you've got the cell science system, CMA. Each of these panels, they all have their own problems. Even the oligo scan has certain problems as well. Most of these are things that can be resolved algorithmically, but some of the tests are not so manageable. So I'm going to come back to the oligo scan because it's really important later. So in the context of how these minerals are affecting the metabolism, it's important to understand that when you're looking at the proteome, so if we're looking at essentially the way that the cells behave, we have essentially the code. So we have the DNA, and then we have transcription, and then we have the proteome. And then we have ultimately not just the proteome, we have the metalloproteome. So there are somewhere between, at the moment, 2,600 and 2,700 enzymes which require a mineral, usually divalent mineral, as a part of the catalytic behavior. So ultimately, if these minerals are low, then the enzymatic behavior is low, and then you might see various different compensations for that as the cells try to kind of accommodate that. But ultimately, progressively, as the minerals get lower, you're going to see more and more progressive reduction in the metabolites that they would normally produce. But also, you might see some hotspots, particularly when you're looking at the pathway map with the patient data. When the downstream enzymatic reactions are inhibited, you'll see a bottleneck. So I'll show you what that looks like in a moment. Overall, though, we can see that there is this cascade present. This is, again, using patient data where we see this pattern occurring. So we'll see problems with the TCA cycle. We'll see different things being shut down, different pathways. The oxidative pentose phosphate pathway is critical, and I'll go over all of that in a minute. And ultimately, the glycogen storage. So we see a progression into sympathetic overdrive. We see a loss of the glycogen. We see a loss of parasympathetic. And essentially, we see a nervous system that sees the world as a scarier and scarier place, because ultimately everything that's being sent to it is a progressive alarm. So you end up with somebody that has anxiety / everything else, or they get to the point where they have problems swallowing and gastroparesis, because essentially the parasympathetic signaling is not there to allow for the pharyngeal contraction and the GI motility. And so that's when you're looking at the severe ME/CFS patients, long COVID patients, vaccine injury, et cetera, et cetera. Part of this cascade is interesting because of the microbiome adaptations. So one of the things that's really interesting is that you'll see over and over again, when you're looking at the microbiome data, you'll see overgrowth of fermenting species. That's going to be your strep, your staph, your E. coli, your Klebsiella, Candida, Aspergillus, a whole range of other species that all produce alcohol and or acetaldehyde. Sometimes as pairs, you might find some produce the alcohol, others will then take the alcohol and produce the acetaldehyde. That has an effect in the body of altering the dopamine metabolism and producing a whole range of opioid metabolites. So you'll start to see that in the literature, in Parkinson's and a range of other end-stage diseases. But ultimately, what happens is that the body starts producing these opioids, and then what happens is that the sympathetic overdrive, so that's the adrenaline through to CAMP-PKA pathway, ends up becoming regulated, I believe, by the endogenous opioid cascade. So progressively, as the NAD to NADH ratio is not being maintained, it then inhibits the ALDH, the aldehyde dehydrogenase enzymes. There are other factors that go into that as well, like, for example, if there's low zinc and other things. And that progressively means that the dopamine and dopal will react with each other, or the dopamine and directly with the acetaldehyde will react with each other to create salsolinol and then a pathway through to morphine. So the body will produce morphine and a range of other opioids as a mechanism to try to balance this. So what that also means is that as you start correcting some of these pathways in the patients, they're going to go through endogenous morphine withdrawal. So all the symptoms of somebody that's getting off, say, OxyContin or something else are going to be seen in those patients as you start improving their NAD redox. It's a critical piece. One of the things in the data though that you might see, so this particular patient, it doesn't actually look like the microbiome is a big factor. The CAMP-PKA is actually elevated at this point, but we can still see that there is a deficiency in DOPAC, despite the fact that we actually have elevated L-DOPA in this particular test. So the data on this is pretty good. We can see that we actually have, histamine, for example, is quite high, so that's going to be dysregulating some of the dopamine metabolism depending on the cell context. But we can see that ultimately there is a dysregulation in this dopamine pathway, and if we were then to look at the other causes for this, we'd find this elsewhere. So I'm going to just jump out of that. There's a lot more on that topic to look at. The retinol metabolism. So this is a simple pathway. When we're looking at the NAD redox just before, it's really important to understand that the NAD redox is pivotal for the vitamin A metabolism. So the vitamin A metabolism starts off with some kind of retinol ester, which then goes to retinol, and then the usual alcohol to aldehyde to, in acetate type metabolism. In this case, it's retinol, retinal, retinoic acid. And then the retinoic acid in all different forms, it actually has different effects on different pathways and different systems. So one of those things could be the PPAR, which is going to be some of the energy regulation. The other one, which is really important is for thyroid function, is NIS. So the iodide transporters require active vitamin A to uptake the iodide into the tissue, which is then required to produce the T4. If the iodine is low, and you'll see that quite often in the oligoscan data, for example, the expectation is that the vitamin A and or the NAD redox are inhibited, which is leading to low NIS activity, which is then leading to the low iodine uptake. And so if you want to restore the iodine in those patients, you can't just throw lots of iodine at them. You're actually going to have to make sure that the NAD redox is corrected, which means dealing with the oxidative stress inside of the thyroid tissue as well. So a lot of the things that we're just talking about with the glutathione metabolism is actually going to have an effect on the retinoic acid and then ultimately the iodide uptake. Broadly, we've looked at some key parts of the cascade. I might take a big step back and then look at some of the tools, and then we'll dive back into it. But what I did want to illustrate there was there is an overall logic to all of this cascade. And look, now that you've kind of seen some of these mechanisms, what you'll then be able to do is, as we go forward in a moment and start looking at the tools, is then perhaps start correlating some of the patient data to these and go, start having some of these light bulb moments and say, oh yeah, I can see that pattern now. So I don't expect anybody to remember, probably even, probably 60% of what I've said in the last half an hour. It is recorded though, so you'll have an opportunity to go back and look at this. So that's my hope, is that this will continue to provide value over the next few days and weeks. Sure. Taking a big step back, so oligoscan and intracellular testing. So oligoscan has a certain algorithmic flaw, and that algorithmic flaw, and it took me probably a good 2 years worth of staring at their reports versus white blood cell to collect enough data to actually go, okay, there it is. I could start to see there was a problem. There was value in the test, but it was just bizarre, because initially I was looking at the hair toxin mineral analysis data versus the oligoscan data. I'm like, well, these are like chalk and cheese. I'm looking at two very different things here. This doesn't make sense. And initially I was thinking, I'll stick to the HTMAs. And then once I'd actually continued reading and understood that the hair, the cells that are producing the hair follicle don't have those transporters, the light bulb went off and said, okay, this makes sense now why the hair testing doesn't actually give us the data that makes sense. So I thought, okay, fine. So we then started looking at all the different white blood cell data and started comparing that to the oligoscan. And that was a lot more congruent. We could actually see the overlap between the white blood cell information and the oligoscan information, with one exception. I started seeing this pattern where things that were high in the oligoscan were showing up as low in the white blood cell data. I thought, oh, that's very, very interesting. Maybe there's some kind of, something strange going on there. So what I progressively saw with the data is that we would see people where they would be progressing. Say they're not supplementing zinc as an example, or it could be many other things. You'll see it progressively get lower and lower and lower, and then suddenly flip and suddenly be high And then if you start supplementing it, you see it then flip and then go lower again and then come back up to the center. So that was the first indication that maybe there was something wrong on the upper levels of the oligoscan data. So I started focusing on that. And progressively what I found out there is somewhere, and I'm still not 100% convinced that I've got it absolutely perfect, but it's pretty close, somewhere between 11% and 14% in the elevation of the oligoscan data is where the flip is. Anything below that kind of range, you can safely assume is an in-range elevation. Anything above that, you can assume is actually an insufficiency. So what I've actually done with the tool that's on the Born Free website, and shortly it'll be in the CSI website as part of the whole the package that all the clinicians get access to, is an interpreter, which then takes the oligoscan report, feeds it through the interpreter, and then removes the iron and the calcium data. Those two, unfortunately, I could not find any kind of correlation between that and any other data. The best I could say is that there's just two faulty markers, so I exclude it completely from the report. Everything else, basically, if it sees that pattern where it's elevated, it actually flips it to essentially an inverted. So the higher it is, the lower it actually is, and that was basically matching the data that I used to build that algorithm. I mean, it's just bizarre. It is such a disruptive technology, and yet they haven't taken the last steps to really put it into clinical practice, and that's where it's at. So I mean, Apple has seen, the use of that particular methodology. They're trying to bring that into their Apple Watches for glucose monitoring. So there's the tech itself is there. It's just that they haven't taken the last few steps to actually, get it to where it needs to go. So
Josh, just what you're saying is you were reconciling the oligoscan with white cell data. And when you say white cell, do you just mean a blood test?
No. Oh, well, the white blood cells specifically extracted from a blood test, and then using those cells as a method to actually explore the levels of the minerals and the metals. So the reason that we're using those and not, say, red blood cells they don't have mitochondria, they have a different role. More often than not, you'll see the elevation in the red blood cells when there's actually deficiency in the white blood cells. So they kind of act like a sponge for the serum, like a temporary storage, and then they're supposed to recirculate those things again. So when you have different inflammatory cascades that are essentially kicking it out of the white blood cells or blocking it from entering it, you'll see a bump in the red blood cell data at the same time as the white blood cell data is low. The Vibrant Wellness test it used to be a lot easier, I think, to show that, but they were showing like red blood cell, white blood cell serum values for the same nutrients, and you could see that pattern time and time again.
And you find the calcium and the magnesium are negligible at the moment. You think they're just faulty markers?
Oh no, calcium and iron are faulty. So the magnesium is fine, the phosphorus is fine. The calcium, I don't know. I'm hopeful that there's something I can see out of the calcium. There's some glimmers of that. At the moment, I couldn't trust it enough to use it. I just essentially removed it from the report. The iron had absolutely no relationship with anything. I have no idea where that marker is coming from. I did explore
what's your preferred marker for iron at the moment if you had to choose any type of testing method for it?
Normal blood, so I'd use ferritin, transferrin, saturation, transferrin, iron, and then you can at least have a look at it. I'd like to see a TSAT of around 40 as like the anchor point. Anything progressively lower or higher indicates that there are problems. And then you can use,
thanks, appreciate it.
Serum electrolytes, not so good at all. By the time you see low levels of the serum electrolytes, they should probably already be in the ICU. So it's you don't have that information. But the white blood cell data is amazing. Like you can see quite significant differences between, say, serum magnesium and white blood cell magnesium. And even then, this is a proxy. It doesn't tell us what's going on in the brain, the liver, the kidneys, but it does give us a pretty good idea.
Yeah, I'm not familiar with a white cell option in Australia. Is anyone else using that? Because I've never used that. And I did, like you, I stopped doing HTMA because I started to feel quite despondent with how to interpret the results.
Yeah, if you use them as a low tide or a high tide and excretory data, you can still get value from them. But it's just understanding. If you see something that's really, really low or something that's really, really high, they're both indicating that there is a problem with the transport somewhere. So it doesn't really tell you what's going on other than, hey, you've got probably an inflammatory issue here that you need to go and investigate. So all of the information that I've ever found online with people with the ideas, oh, you balance this and you use this to do that and you do that to do this. I haven't been able to kind of correlate that to what's going on with the white blood cell data. So if I was to pick any of the white blood cell data tests at the moment, none of them are perfect either. So The one that I do kind of like, but it doesn't work with the more severe patients, is the Cell Science System CMA. Challenges with that, it's got to be on like a rushed FedEx, which they will include as part of their package to get it to the States. That got problematic in recent times with some of the border changes with the US and things, but still there. The problem, the way that panel works is essentially they take the white blood cells, they replicate them, and then they set them up in these little micro wells and throw single nutrients at them over and over and over again, to then look at the response and the metabolism. I think they use certain things that they calibrate against. And so if you, for example, added magnesium or choline or something into that cell, and you see the metabolism ramp up, they then say, okay, well, we saw an increase of 40% or whatever, so therefore there was a 40% deficiency against like whatever their calibrated baseline. The problem with that is that cells are complex. And so if, for example, you've got very low phosphate, and all the phosphorylated metabolites inside of the cell, you might add a little bit of magnesium, or you might add a little bit of like whatever, there's a whole range of markers in that panel, and it doesn't move. It's because the cell's being bottlenecked by a much larger, much more important restriction. And so the test that comes back, you get the results, and the patient looks normal. You're not seeing all the deficiencies. Yet if you were to look at all the metabolite data or anything else, you'll see a great range of deficiencies. So so that's the limitation. I've written them. They've been much less responsive than oligoscan.
So for now, within Australia, if we were doing testing, it's really the OAT and the oligoscan that we would enter into your software.
Yeah, well, actually, I'd suggest sign up and get the Theriome. If you've got patients with the budget, get the Theriome account set up, and then you can get up to 296 analytes instead of the usual 77 out of the Mosaic. I'll show you the difference, actually. Let me just jump into the...
Yeah, I haven't heard of Theriome before. That's new to me.
Yeah, sorry, just change. So, let's have a look at this. It's a big diagram. It'll just take a moment. Laptop here struggles with this one a little bit. Okay, so this is figure 1 using Theriome Classic. So all of the colors that you can see, it's looking like a Christmas tree. These are all markers that you can actually click on and you can see values, but at a glance, the colors tell you what's going on. So if it's red, it's high. If it's dark blue, it's really low. Green is kind of good. And then you've got all the different ranges in the heat scale. So when we're looking at so if you wanted to look at the citric acid cycle, you can say, okay, well, citrate was kind of good, and then we can see there's a drop at isoconate, and then we've got an elevation of D-isocitrate. And then likewise, you can see, hey, there's this elevation of malate. So just even at a glance, I mean, before you even look at the NAD and NADH, you can say, hang on a minute, these dehydrogenases are actually going backwards, which is what they do to try to regulate the NAD balance. So oxaloacetate's going to malate, alpha-ketoglutarate going to D-isocitrate. With the Theriome, the Aristotle Plus, you get direct measures of the NAD, the NADH, the NADP, the NADPH, the ATP, a range of different things that you normally would try to calculate. So it's a really exciting test to use. It takes a lot of the guesswork and calculations out. You can then also start looking at things like say like the glycolysis pathway. We can see bottlenecks here. You can see, for example, we've got G6P and F6P are elevated. And that's giving us a pretty strong indication that we might have a zinc and an ATP deficiency, or we might have elevated fatty acids or something, which are actually creating an inhibition of the PFK1 and 2 activity here. And then ultimately,
I have a pediatric client with a homozygous SNP for G6P, and poor kid can't break down glucose. Ooh. But we don't have something like this for him. Like, it's been very minimal, the testing.
Yeah, well, and look, this isn't even the best data. I could show you just in a sec. I'll just clear the files and I'll open up another example. If we were to look at a plus, I will just bring up that, and I'll grab some mineral data in here as well. In a moment.
It's much better analysis of these tests, isn't it? So then your script is going to be way more targeted.
Yeah, well, there's so much more to show. So the thing is, I don't expect people to have the level of biochemistry knowledge which I've acquired, because it's one of those things. If you spend all day doing this, sure, you'll get to that point. And if you've got 15 minutes to deal with a patient, you're not going to be able to do that. So what I've got is a tool that will do all of that for you. So for example, it'll look at all of the oat and the olig and all the other data, and it'll come up and it'll tell you, hey, look, here are the headlines here. You know, these are the problems that we're seeing. These are the things that you actually need to look at. And so it basically takes the work out of it for you. If we were to look at that glycolysis pathway again, I'll just zoom in. Okay, so a couple of things to just fundamentally understand. This branch off the glycolysis pathway here to serine and phosphatidylglycerine, this is essentially a sensor pathway, right? So this basically detects if there is enough glycolysis to give us 3-phosphoglycerate, but then it also tests for the NAD redox, it tests for the TCA cycle status, so essentially the glutamate to alpha-ketoglutarate, the P5 status, and then ultimately gives us either phosphatidylserine, which then regulates the hormones, serine, which then regulates the glycolysis, so PKM2, but it also regulates methylation and transsulfuration. So if you have low serine, it essentially is shutting down the methylation and everything else because there is not enough flux, or there are different faults, and basically these feeder pathways need to become inhibited. So when we look at this pathway, we can get a bit of a hint and say, okay, well, hang on a minute. We have relatively low glucose in this one. We have elevated G6P. We then have, despite the fact that we have this elevation, we then have low fructose 1,6-biphosphate. So that's showing us that there is some kind of bottleneck here, which we can also see from the mineral data is a severe zinc deficiency. But likely the MGATP is going to be a problem. We can see it start building up again. So it's low at glyceraldehyde 3-phosphate, starts building up at 3-phosphoglycerate, really builds up at PEP. And then if we were to sort of take a little sneak peek down and have a look at pyruvate, we can see that despite there being really, really high PEP, we've actually got really, really low pyruvate. So that gives us a really strong indication that pyruvate kinase M2 here, which sits between those two, is inhibited. And it's essentially regulated by the serine, the potassium, magnesium, fructose 1,6-biphosphate, gets inhibited by oxalate and lead and various other things. So if we are looking at this, essentially the serine is downstream of these different tests as a fault sensor. So low serine equals low blah, blah, blah. So the various different pathways downstream. So low glycolysis, low methylation, low transsulfuration. So it's basically indicating, hey, there's a problem here, calm it all down until we can recover. And then at which point the serine levels come back up, and then the rest of the pathways get restored. So this level of detail is great. So we get a direct measure of the NAD. So just confounding this data, the person was taking sublingual NAD and they're taking glycine. So just putting that into context, when we actually look at the NAD, if we look at it, so we have an actual measurement of saying, hey, look, there's actually 53% elevation in NAD. And if we look at the NADH, we can see that there's actually an elevation 284%. So despite the fact that there is like the total NAD to NADH pool is highly elevated, it's all the redox, right? So it's all stuck as NADH and not enough NAD. So everything that requires NAD to NADH is being inhibited. Hence the reason that we can have a really high 3-phosphoglycerate. And even though the transamination here would absolutely be working, there's not enough flux through this dehydrogenase to actually allow it to happen. So we still end up with low serine and then everything else being shut down. So this level of data and these tools makes it really easy to visually step through and see what's happening. You can see the bottleneck, and then if you're overlaying the oligoscan data with the analytes, you can look at the mineral cofactors and other things to actually understand why these things are low. It's no longer guessing, and it's not just numbers on a piece of paper. So then it becomes really actually quite clear what's happening. So we can look at, say, the pyruvate and say, okay, well, yeah, that was really low. We can see the lactate's really high. And then, yeah, we get a feel for the, what the metabolism's actually doing. Likewise, we now have a direct measure of the oxaloacetate. So we can see that's really low. We can see the malate's really high. We have direct measure for the NAD being, high, but the NADH being higher. So we can see perfectly, yeah, actually, yeah, all of that is definitely running backwards. Oxaloacetate is low, malate's high. That's going to have a knock-on effect if this was coming from the liver of actually inhibiting the gluconeogenesis. So in other words, the glucose outputs of the serum is going to be inhibited at this point, regardless of whatever the thyroid or cortisol signaling is doing. So this person is going to have quite a few issues with brain fog and fatigue and various other things. we then have, a lot of resolution over the glutathione metabolism. So we can see in this case, even though we've got low pyroglutamate, which is kind of the only dashboard marker that we get in the mosaic and the other oats, we can see that because we have resolution that includes glutathione reduced and glutathione oxidized, we can see that what's actually happening here is the bottleneck is actually here. So the redox from the glutathione oxidized to reduced is being inhibited somewhere. So, well, what's going on with that? Is it the high cadmium? Could be the high cadmium. Then we can actually have a look, a direct measure of the NAD pH and the NAD P, and say, well, hang on a minute, we have really, really low NAD pH, so that's negative 475%, but we also have very low NAD P, so negative 700%. So in this case, the total NAD P to NAD pH pool is low. So that's giving us a pretty good indication that the conversion of NAD to NAD P is being inhibited. So this then goes back around in a circle and say, well, actually, hang on a minute, just a moment ago, we saw we had elevated NAD, right? So there should be plenty of NAD to convert into NADP. And then we start looking at the NAD kinase activity and say, all right, well, maybe there's really low magnesium, maybe there's really low ATP. And so then you say, well, that's actually been directly measured. We do have very low ATP and we do have very low magnesium. And then you would then look at the rest of the pathway and say, okay, well, that's looking like the glycolysis pathway is being inhibited. So the first half of the first half of the glycolysis pathway is a net ATP consumer. The second half of the glycolysis pathway is a net ATP producer. So that low zinc here is preventing the magnesium and the phosphate uptake, and then ultimately the cytosolic ATP generation. So this is what's actually creating a huge cascade of issues. But ultimately, this is then leading to all of the other things that we've just been talking about. So this person would need to fix their zinc deficiency before they can fix their magnesium and phosphate deficiency before they can then work on everything else.
Josh, do you ever reconcile this with my DNA or something else, just to see if someone just needs to be, for example, prescribed sublingual liposomal glutathione, if they've got SNPs that are just really not in their favor, or do you just prefer to see the live data?
It's a bit of both, but look, the SNPs, I'll be honest, rarely have value unless they've got an inborn error. And if they've had like 10, 15, 20 years of normal metabolism and then suddenly they've fallen off the cliff, then the genes aren't driving it. They're only essentially, they will be coloring the situation while there is a metabolic challenge. But they can also be part of the situation that leads to like the predisposition. So for example, somebody that's got NTHFR and related SNPs, then basically that zinc deficiency that might be leading to progressive loss of the cysteine and the glycine, and then ultimately this mess with the glutathione metabolism is going to be enhanced, because essentially that, negative 30% in metabolism or processing here at NTHFR or the others is going to be equally affecting the outputs here at glycine and cysteine potentially. So that's the predisposition, but it doesn't drive it. It doesn't create it. It only colors it or allows a predisposition. So you're not going to do anything to treat the genes, and at the end of the day, the metabolism that you're working on is going to be restoring that, this back to at least where it was back when they were functioning.
Okay, that makes sense. Yep.
Yeah. So a lot of these practitioners who are just taking the SNPs and then putting people on a protocol that they just stay on indefinitely. You're obviously in the camp of we don't do that. We kind of wait to see what expresses and then we deal with it as it comes along.
Exactly. I mean, look, the body's not stupid. And look, epigenetics ultimately will upregulate and downregulate expression of these proteins to compensate. So that's the thing. Like, and look,
again,
I
see that so much with the methyl Bs. Everyone's just methyl being people to death. And people are over methylating, and then you've got practitioners going up and down with it all. And it's interesting because I've had this discussion a lot with people about over prescribing and over treating.
And the methylation has a big impact. So when we talk about over methylation, really what we're talking about is under production of the neurotransmitters and relative to the degradation pathway. So when you're looking at the methylation, sure, we have creatine and other outputs, but what's ultimately you're looking at the SAMe, which is going to be needed for COMT. And so in that context, if you start fixing up COMT and you start then improving the degradation pathway, if you still have bottlenecks on the synthesis pathway, you're now creating a net neurotransmitter deficiency. So this is why there is this balance that needs to be restored. You can't really do a whole lot with the methylation until you've done that. But there's also another big piece. So if you start fixing up the methylation and then you start fixing the essentially the glycine and the cysteine essentially on the other side, and then you start fixing up the glutathione metabolism, it has a huge effect because the glutathione metabolism is also the NADP or NADPH redox partner for something that's really critical, so the oxidative pentose phosphate pathway. So in other words, if the glutathione metabolism is inhibited, the pentose phosphate pathway is inhibited, we end up with low PIPP and R1P, which then means that we have low, ultimately, the glycogen synthesis, and we have low inosine synthesis and NAD synthesis and various other things. So what that means is that if you start fixing that methylation to glutathione metabolism, you're now going to affect the insulin insensitivity. You're going to improve that. And that means that you're suddenly going to start seeing hypoglycemia type symptoms. So that could be, all the things that you might expect. Because essentially, if the thyroid signaling isn't keeping up with the insulin signaling, then you end up with lulls, little drops in the serum glucose. So the insulin sensitivity improvements then end up creating a deficiency temporarily. So this is why getting the thyroid function up ahead of any of the work that really touches methylation and glutathione metabolism is so important. Otherwise, you're going to run into this seesaw balance, essentially creating new symptoms. So that's a fun topic, but there's other layers to that as well. So we've got to look at the hepatic gluconeogenesis, substrate pathways, and it's probably a topic for another day with, fresh brains and not overflowing from information. So there's a lot ultimately that we can do. There's discussions around hormones and things. We didn't touch on any of that just because time limitations and there's only so much information perhaps in one day to process. But the hormones are both upstream and downstream of everything in the cascade. So they regulate a lot of the energy metabolism and the immune system, but they're also regulated by the mitochondrial dysfunction and some of these states. So if you look at this, essentially, like the NAD and the NADH metabolism is directly responsible for how some of these things work, and then that ultimately leads to regulation or dysregulation of some of the immune response via the cortisol. So there's essentially, this is part of the sensory feedback. If there's too much tissue damage signaling, if there's different problems with the mitochondrial metabolism, the hormones then end up adapting around that situation so that you don't end up with cells blowing up from excessive energy metabolism and oxidative stress or tissue damage. So this is why people that go on exogenous hormones for various reasons in HRT, there might be some benefits, but you also then might see blood clots and immune, response that might be, out, or you might see, potentially oxidative stress, dysregulated immune response in cancers and things like that as well. So all of these things kind of need to be balanced. And so if you're going to, remove this regulation, then you ultimately then need to, provide it yourself and balance this out on the other side. So anyway, interesting. But ultimately, the mechanisms are there if you want to explore.
Thank you. This was brilliant.
It really is.
Brilliant. Really. And your generosity to share this information. I know that a lot of us will, certainly be extolling the virtues of the software to anybody that uses oligoscan and oat testing. So I know even for me, oat testing is still a bit of a challenge after all these years. I don't think it's straightforward for too many people. It's probably a few.
Unless you've got like the big subway map of all the pathways, it's like it's just information overload.
That's
like
right.
The last hour of information, for example. But that's what.
And then you're looking at that in context of all the other things that you've got to look at, microbiome tests and what have you, and it does get really burdensome. So this is a fantastic tool. Well done.
Yeah, there's a microbiome tool on the website as well, but that's just for the biome site, and that's going to be updated a little soon enough. But essentially, it'll show you the fermentation versus other things. Anyway, there's a lot to cover, but today was, I think, a good. But
thank you so much, Josh.
Thank you.
Really
thank you very much.
Time. Speak soon.
Thank
we'll
you.
put a poll in and get the next one on the schedule for everybody.